Okay, so starters, the midterm is already up on Blackboard. You probably got a kind of announcement or notification, email or something like that today. Is that a true statement? Got something? I made it due Wednesday by midnight. There's no time limit, but make sure you do it all in one sitting. Closed book, closed note. You can use a calculator. Don't work in teams. All that good jazz. I'll make sure that I am available live during class on Wednesday, guaranteed. If you want to set aside that time to take the exam, you can ask questions. Otherwise, I'm pretty available on Slack anyways. But you can take it whenever you want. Just make sure you get it all done in a single sitting. All right. So an interesting phenomenon is if any of you have ever been like on a boat for a prolonged period of time, when you get off the boat, you kind of feel like the world's kind of rocking a little bit as you're walking around until you get your sea legs, something like that. Well, so this weekend I finished beating one of the VR games called Lone Echo, where you do the entire game in zero gravity. And now there's a sequel called Lone Echo 2 that I'm playing through. Super good game. It's on the Oculus store only, but it's PC based. And so now my entire world is like, feels like it's kind of off. And I find myself like looking for handholds and stuff like while I'm walking around the world. And I want these little boosters. Like I want this to be real because you got these little boosters. So you're like making these little adjustments and things like that. And I want real life to be like that. And I've spent a decent part of, well, mostly last night. Got my bearings back now. Viewing the real world as that zero gravity world. So kind of an interesting psychology of full immersion, I guess. Tech news, Apple does have a announcement today at noon. I think they're announcing new MacBook Pros, things like that. Should be an interesting announcement because they're going to be talking about their next generation processors. So whether you're a Mac person or not, doesn't really matter. One of the interesting things that's happening in the tech world right now is a shortage of chips, and Apple makes their own silicon. So these are chips from Apple that have pretty crazy battery life and stuff. This laptop here is running a Intel Core i9, so this is not battery friendly, this laptop, but I have a MacBook Air that's running an M1 chip that basically never runs out of battery life. If I get on a Zoom meeting with this at the end of an hour, I'm probably at like 65%. If I'm on the MacBook Air doing that same Zoom meeting at the end of an hour Zoom meeting, it's at 99%. It's really ridiculous, the battery life on the M1s. So that'll be an interesting announcement. I imagine they're going to be announcing MacBook Pros with like, 35-hour battery lives and that and that kind of stuff. All right. And I think later on this week is Facebook Connect, their announcement, which should be kind of interesting. That'll be VR specific. Last week was HTC's Flow. There's a couple other tech companies, bunch of tech announcements here at the end of October. Very exciting tech time leading up to holiday gifts, I suppose. All right, so last time we, or at least 2 times ago, I guess, we briefly talked about AVL trees. Well, I guess before I go on, does anybody have any questions about the midterm or anything they want me to review or anything before we just keep trucking? The stuff we're talking about today is not on the midterm. This is just kind of preparing us for the next step. All right, so we talked about this idea, and I mentioned that we're not going to actually implement the AVL tree, but we have this concept called tree balancing, where the idea is if you have a binary tree, one of the reasons you're storing things inside of a binary tree is because it stores it in a sorted manner, and therefore searching within the tree has a benefit. All right, because it's already stored in an organized fashion. That being said, to give yourself the best average search time, that tree needs to remain relatively balanced, meaning one side can't be too lopsided from the other side. So with that in mind, and we had already talked about that we're at the mercy of the order in which data is added to the tree, in terms of creating what shaped tree we end up having. You could take the exact same 1,000 elements. I think didn't we run that at the end last time? Let's see. There was an issue at the end of last class. Just copy this code. Or I guess the previous link I had shared wasn't updating. And then when I went to do this on my laptop, I had to just rewrite what we wrote in class, but there is the updated link for our get depth for our binary tree. This is the same implementation we had before, but apparently our original one wasn't updating. It's probably one of those weird save things. But in any case, right here, what I did is I went ahead and I just generated a bunch of random numbers. Have we done that in class last time? I think we generated random numbers in class last time. So I just created random nodes and I added them to the tree in just some sort of order. All right. And when we run this, we should get the depth of our tree for those 100 nodes in this case. This is my So that guy has a depth of 12. Another depth of 12. Depth of 14. So we see there is some variance, even though I am presumably creating different numbers. And actually, this is an interesting way of actually testing the how good your random number generator is. Because if you get presumably this is a fairly balanced tree. All right, so if it has a depth of 14, keep in mind that the top level is 1, then 2, then 4, then 8, so on and so forth. If you do the math on this, you actually get a tree that's not too terribly lopsided. We can get the, let me go into, I'll take out display in order because that obviously is working, and we'll print out get depth. But what I'm going to do is inside of our binary trees get depth. I'm returning the depth of the root node, which is going to be the depth of the left and right child. So what I'm going to do is I'm just going to ask a question here real quick. If I'm not going to be able to do that from within here. What I want to do is I want to show you the top level of the depth of the left tree and the depth of the right tree. So let's go into here. We're going to do this. If the left child's a thing, we'll do a C out. Left child, get depth. If right child is a thing, we'll do a C out, right child, get depth. And then we'll call our normal get depth on this. So I've just written a secondary version of get depth that takes in an integer for no good reason other than just to differentiate itself from the first one. So I'll go ahead and add this guy in here. So now the idea would be if I'm in binary search tree and I call get depth, I'll actually just pass that guy. I'll call the version of it that takes an int only on the root node. So that'll come in here. It'll call this one and it'll print out his left and his right child. So this is only going to be the root node who will say, my left child has this depth, my right child has this depth. And we're going to see how balanced the tree is just by random default. Then he calls his normal get depth that actually does what it did before. Okay, but this is only going to happen at that top level where the root node is going to report what his left and his right child have in terms of depths. No return statement in there because I don't actually return it. Make sure I return the value because that's what that guy was expecting. Oh, let me kick it down a line. All right, so we have a left of 10, a right of 10, a left of 11, a right of 10, total depth of 12 because it's 1 plus the maximum of the left and the right. Run it a couple of other times. Oh, actually, that was a bad one. I clicked, yeah, here. So you see, this guy's pretty left heavy, the tree that got created here. And that has to do with just the random luck of how that was a pretty good balanced tree. This just has to do with a random luck. If it generated a bunch of large numbers first, then everything it'll be right heavy before it even starts adding stuff on the left-hand side. So now you've gotten off balance right from the get-go. Just kind of an interesting way of observing the different trees. So we're adding 100 numbers, random-ish numbers, right? And we're putting them in the tree and producing very different shaped trees. All right. With the ultimate idea being, because we can get different shaped trees based on the nature of the data that's going in, even if it's the identical data. In this case, we're not giving it identical data, but we could. But if the order of the data changes, the shape of the tree might change. We might need, for performance reasons, the ability to adjust the shape of a tree to make it more efficient for searching. With that in mind, We have something called an AVL tree. There's several different, actually, let's just look at self-balancing tree. So here's several different approaches to a self-balancing tree. Each one of these is an algorithm that attempts to balance the tree and keep it relatively prepared for searching from an efficiency perspective. Now, one of the things that when we talk about the efficiency, what we're really talking about is the average seek time, the average amount of time it takes to go and look for a value inside of a tree. I mean, because otherwise, even if it's unbalanced, you might luck out, right? You might get a really short seek time. But on the flip side, if you don't luck out and the thing you're searching for happens to be really deep on the tree, but down all the way down some line, you might spend quite a bit of time looking for it. Or even in the worst case, if the thing you're looking for isn't in the tree. All right. So the idea is that we want to give consistently good performance, let's say, or consistently reliable performance on a tree, and that's going to require that tree to be balanced. So the one that I like to look at, and it's probably one of the more famous implementations, is called the AVL tree. Red-black trees are also pretty popular, let's say. Splay trees used to be, I would say everything else there is made up in terms of being popular today. Let's take a look at AVL trees. And I mentioned we're not going to actually implement it. And since I'm not giving you homework over break, this is a good time to look at something like this. All right. Sure, I want to get to my pictures. No, this is actually kind of an interesting implementation. You know, it's showing you an animation of this stuff happening. Tree's balanced, tree's still balanced, only depth is one higher on that side. Out of balance. So see how it's doing kind of almost, I think I referenced it last time, almost like a chiropractic adjustment as we're turning elements of this tree. So we got a new root node there. All right, so that's effectively what AVL does. So every single time we do an insert into a tree, we then ask the question, is this tree out of balance? And we ask that question based on the left and the right depth off of the root node. Things we just showed a minute ago where I'm printing out the left and the right. All right. And if it's out of balance, we potentially need to make an adjustment. Sometimes if it's only out of balance by one, we might not be able to make an adjustment right now without it effectively always being out of balance, right? We might change it, now it's still out of balance. You change it back, it's still out of balance, so on and so forth. So we make attempts to shift the thing into a balanced position. And the magic here happens at the insert level. When we add something to an AVL tree is a superset of a binary search tree. So an AVL tree is a binary search tree that adds the additional ability to his insert function that says, I will make sure that I'm as balanced as I can be after you insert a value. That's what it says. All right. So it's not a brand new kind of tree. It's just a binary search tree that does a little bit more. Used to be some pictures that showed the so these are talking about the four things, and hopefully there's some visuals down below. But these are the four things that could be wrong. Okay, so a right violation where Z is the right child of its parent X and the balance factor of Z is greater than 0. Balance factor being how out of balance it is. That's a right violation. Here's the right correction. So X is rebalanced with a simple rotation following this thing called rotate left, which I'm guessing down below is the figure 2 that they'll talk about. So if this is the joint that's out of whack at the chiropractor, this is the correction. If left is what's out of whack, the correction is a simple rotate right. These first two are relatively simple fixes to the tree. It's this guy right here, this right-left out of balance, where Z is the right child of its parent X, and the balance factor of Z is less than 0. So this is a different violation. And the fix to that is a more complex repair. And that is we rotate right, then left. It's a kind of a double movement. Same thing left to right, left, right as a left, right fix. It's a more complex change. So this is showing those two simple rotations, the right, and the left, left. So it's showing what actually happens. So this is a, I guess this would be a right, left, right? So this guy becomes the new, so this is the out of balance. Z becomes the new root, X drops off it. Now what we're seeing here is actually, when we look at this tree as a whole, we actually say, well, he's just as out of balance as he was before, right? Visually, this tree and this tree are the same level of lopsided from a human being perspective. It's the violation that took place within the tree, right, or left, left. So this guy is a simple rotate left fix. So rotate left fix is what we do when we have a right violation. A right violation is when Z is the right child of its parent X, and the balance factor of Z is greater than or equal to 0. Z is the right child of its parent, and the balance factor of Z is greater than or equal to 0. So this guy has something greater than 0 hanging off of it, but he's the right child. So really the problem with this guy isn't that the tree right now is horribly out of balance, is that the tree's current state puts it at risk of becoming more out of balance. Does that make sense? And that's why we say this is a violation of the AVL tree rules, one of the 4 violations. And because of that, we will do our rotate left correction, where we rotate this node to the left. I kind of think of it like turning a doorknob or something like that. Okay. So even though the result here looks just as out of balance to us visually, it's in a better position for in preparation of the next insert to maintain this balance factor. Now these double rotations, so this is a right-left double rotation. That's this rotate right-left. So X is rebalanced with a double rotation. So our violation here is this guy right here. Z is the right child of its parents X, and the balance factor of Z is less than 0. This is my simple left. Actually, let me go up and show you the balance factor stuff. No, we'll do it. So balance factor is defined by the height difference. So right subtree minus the left subtree, right? Specifically the right minus the left. So if we come back down to this guy, the right subtree has a depth of 1. The left subtree has a depth of, let's say, 2. Depends how you want to count. 1 minus 2, less than 0. Make sense? That's why we're in that. So that's a negative value. That's why we're looking at this violation. The Z is the right child of a parent X, and the balance factor of Z is less than 0. The left subtree of Z is deeper than the right subtree of Z. All right, so we're identifying that weakness, let's say. All right, so in this case, Z is the right child of X, and Z's left subtree is deeper than his right subtree. That is the balance factor of his right subtree minus the balance factor of his left subtree, at the depth of his left subtree is less than 0. So we look at this guy and say he's out of balance. Even though we look at this visually and say, oh, well, that tree isn't that lopsided. Okay, it has less to do with the overall tree and more to do with the risk factor within the tree in preparation for the next insert. And that's why AVL trees do their rebalancing act as part of the insert operation, which you can imagine is not overly efficient, right? So inserting into an AVL tree takes time because you presume that, hey, there's a decent amount of time, especially in a situation like this where random luck puts us in a situation where we might need to do some adjustments within our tree when it really didn't look that bad. Does that make some sense? Well, so then why do we do it? Why do we rebalance the tree? Well, it ultimately comes down to what's the rationale for us using this tree. Why did we choose a binary search tree as our data structure? Well, it's probably because we're going to do something with that binary search tree. We're going to talk about an application of it here in a few minutes, but we're going to do something with that binary search tree. And because of that, having it in its most optimal format, even if the cost of building the tree was great, gives us more bang for our buck moving forward. All right, because a lot of times the idea is that we're reading in from a data set initially, and we're not necessarily adding tons of data to our tree as we go. Instead, what we're doing is we are probably doing searching on our data pretty often. Could be a core component of a database or something like that. And even if we do add data to our database somewhat often, so data does get added to this tree, an individual adjustment isn't all that complicated. It has more to do if we're adding 10,000 values to a tree and we're constantly doing these little manipulations. It feels like I'm working pretty hard to put my data in this sorted format. Is it really worth it? Well, ultimately it comes down to how often you're going to search that tree later on. So definitely a specialized rationale for doing this type of thing, but not a non-existent one. All right, so in a right-left rotation, we notice that we have a violation here. So what do we do as a result of that violation? Well, we do a right rotation first. So notice that this Y comes up and replaces the Z, and the Z drops down, leaving us with something like this. And then we do a left rotation to rebalance that tree. So we would say that this does look better than this or this. This looks pretty balanced, right? But that was because of the level of the violation that we had and what the prescribed fix for that violation is. All right. So the reality is that implementing AVL trees isn't necessarily horrible, but because we don't have a great use for it, implementing it is kind of, let's just say it's somewhat of a waste of time for us, because really we're just identifying 4 violations and writing exactly 4 different fixes. And you imagine that each of these fixes aren't necessarily horrific to write, especially these first two. Rotate left, rotate right, they're actually pretty simple to write. And rotate right left is actually implemented in terms of these other ones. So they're not that bad either. It just happens to be that it's hard for us to visualize because we're just saying, hey, what's our balancing act? And let's rebalance. And you ask, what's the balance factor of the left? What's the balance factor of the right? Does it look good? If it looks good, we're going to say it's still balanced. It's just a hard thing to kind of visualize whether or not what we just did solved the problem. And I think it's sufficient for us in here to look at pictures for it and say, okay, I pretty much get it. Trees out of whack, do some manipulation to fix it. Good enough? All right, and then it does all the mathy stuff and says, well, this is the efficiency of this rebalancing thing compared to, if we go back to this previous slide, here's these various implementations of what's considered to be good ways of rebalancing a out of balance binary search tree. Ultimately, they all make sure the tree is in a balanced format and ready to be relatively efficiently searched later on. Okay, so questions about the idea of AVL trees. A fair question on like a final exam would be something along the lines of why is an out of balance tree a problem or something like that. Making sure that you kind of understand from a data structure perspective that trees work a certain way and an out of balance tree, depending on how you're going to use it, could be a problem. Could be an efficiency problem. And we see right here, there's a whole bunch of approaches to it. And presumably when you go to write one of these, if you were in charge of doing it, you would pick the algorithm that you like the best, probably either AVL or red black trees, and move on with life. Or use a built-in tree data structure in one of your languages that's called self-balancing tree or something like that. All right. So next, we're going to talk about something called the heap. Up to this point, how many of you have ever heard of something called a heap before as it relates to computers? Sort of, kind of, maybe. Well, typically we hear two different things in computer architecture. We have something called the stack and we have something called the heap. All right, so the stack typically is a place where things get temporarily stored. So everybody in here has, have we had 325 already? Your organization class? All right, so did you, what's the use of a stack in computer organization? Guess make something up. It should have been a thing in there. Was it a thing in there that we just forgot, or was it not a thing in there? Okay, so it was a thing, but we've forgotten why it was a thing. Is that accurate? And why did we forget? Shouldn't you be encompassing all this knowledge so it's just there forever and ever and ever? But you don't forget your controls on your favorite video game. It's just locked in. All right, so in our computers, we have these things called hardware registers, right? So like kind of variables made out of hardware that sits on the CPU, and we have a finite number of those. So we might say, okay, you know what, I'm somewhat limited on the number of simultaneous values I can store on the physical CPU at an individual point in time. Now, realistically, that limitation isn't horrible when you consider the number of values that I need to have super fast access to. So we could use a portion of system memory to hold on to something called a stack. And we know what a stack is in here, right? Last in, first out type thing, where we can take a value that we are going to need soon, but we don't really need right now. We could push it onto the stack from an existing hardware register, opening up that hardware register to be used for something else. All right. So the stack gives us kind of a additional temporary, but pretty fast place to store data that we're going to need here in a second. All right, without having to write it back to disk at a certain memory address or something like that. It's just saying, put it on hold. I'm going to grab you back in a second. All right, that's how we use stacks. Pretty similar to like how we process the shunting yard algorithm, where we use things, we threw it onto the stack and popped it back off, or we did a push pop to, did some math, threw the answer back onto the stack, that kind of stuff. Okay. So the other data structure that's related to our computing is something called a heap. Now a heap is a fancy word for something called a priority queue. All right, and priority queues are things that we do have an understanding of in real life. We know what a queue is, right? A queue is a line, okay? And we see priority queues if you've been to like Disney World or something like that, where you can buy the fast pass thing to let you cut the line, that kind of stuff, because you're a king for the day, so you have a higher priority. So it doesn't matter where the line is, you get to zip to the front or zip to the farther up. The farther up thing, or if you fly Southwest Airlines, depending on when you checked in for your flight, you get a boarding letter. You're in section, session, A or B or C, and they make you line up in your sections so that you can go and fight for it with your smaller subgroup. Fight for your seat with your smaller subgroup. But the idea is that it's not necessarily always first come, first serve. It's first come, first serve sets the initial structure of that line, but then there's some various priorities that are given within that line, and those need to be managed in some sort of way. So generically speaking, that's what a heap is. A heap is an implementation of a priority queue, and almost always, well, very rarely in computing do we call them priority queues. We call them heaps. Okay, so heap, a data structure follows the heap rule set, just like we follow the binary search tree, the BST rule set. And we'll go and look at this guy. All right, so like I said, we have this thing called a priority queue. All right, and a common implementation, well, like I said, it's almost always called a heap. Priority queue just kind of allows the human being to connect it to what does this guy actually mean. You're in line, but if you're at McDonald's and the president of the United States walks in, he's probably cutting the line. That type of thing. Whether you like him or not, he's probably going to get priority for his Big Mac over you. is the idea. Okay, so we should notice here pretty quickly that this guy looks like a tree. So heaps are implemented typically, they don't have to be, but in our context, we're going to say that a heap is implemented in a tree data structure, a nonlinear linked data structure. Now we have this new concept. I'm going to throw it in the slide right before here, called a full tree. All right, a full tree is a tree whereas many of the child nodes are filled before dropping to another level. All right, so on one hand, we might say, okay, well, maybe this is somewhat of a defense against unbalanced trees, right? We don't let it get super deep on one side. But an issue is that, well, then we kind of are in conflict with our rules associated with our, for instance, binary search trees, where it's like, look, I have a value. This guy has a place he needs to go. You're telling me I can't put it there because there's an empty seat over here. All right, so we do have to make some decisions as to which flavor tree we're going to use for different things. So I want to make sure that we're clear on this idea that one tree is not necessarily better or worse than another one. It comes down to what application we're using it for. All right, but the idea of a full tree is we want a tree that kind of fills out pretty well, and whatever consequences that has for us in terms of what rules we're allowed to apply to that tree, that's fine. In this case, we're going to be applying the heap rule set, which is Sounds kind of like the binary search tree rule set, but it's just a little bit more generic. All right. But ultimately, we're trying to fill out the tree before we drop down to another level. All right. So that's what we mean when we say full tree. All right. So we notice here that this tree is a pretty full tree. We filled in all the stuff. We also notice pretty quickly that while it does seem like the stuff that's at the bottom is smaller than the stuff above it, it doesn't quite fill in the real rules of the binary search tree. All right, so we have something here called the heap property. So heaps come in two flavors. Min heaps, max heaps. Basically the same thing, just the property flips. Okay. For min heaps, it says that the parent node is less than or equal to the stuff below it. Max heaps, the parent node is greater than or equal to the stuff below it. All right. So for a max heap, for any given node C, if P is a parent node of C, then the value of P is greater than or equal to the key in C. So if we want to go over and look at this, notice that this guy right here, this is a max heap. 100 is greater than or equal to all of its children. 19 is greater than or equal to all of its children. 17 greater than or equal to all of its children. 36 greater than or equal to all of its children. That's the heap property. Not everything to the left is less than or equal to everything to the right is greater than. It's only my level versus what's beneath me. Okay, this dude right here is at least as big in a max heap as everything that lives below him. Period. No more detailed than that. All right, so we're good with the heap property. Fairly simple, and you just need to know, is this a max heap or a min heap? And remember, we're thinking about this from the context of our real life understanding of a priority queue. Max heap means most powerful guy goes first. Min heap means least powerful guy goes first. Okay, because if we're doing this as a priority queue, we're probably, if we look at this, the most important guy in this max heap is the dude right there at the root node. So if we think of this as an implementation of our line at McDonald's, whereas people feed into McDonald's, they self-place themselves based on their priority. Or we think about this in computers, where heaps are probably most common. Well, certainly it's where that word is most common. We think about, we have multiple processes that run, as this is more of an operating systems class discussion. We have multiple processes that are running on the CPU, but not all processes are created equal in terms of their importance, right? A couple of applications that the user currently has open, like right now, I have a web browser open and I'm actively using this web browser. That guy should have a pretty high priority for getting CPU time because I'm going to notice, right? Whereas one of my other applications I have in the background should have a lower priority, and maybe some, maybe the iCloud update thing, it tries to get a word in edgewise when it can to, keep the cloud synced or whatever, but not at the cost of the user's experience. Make sense? So in that case, you might have 3 different processes running on our computer, and you might have one that is rarely getting CPU time because it's just not that important right now. We got to keep the user happy so they don't start screaming. So this idea of a priority queue with this idea of heaps, where, if you're at McDonald's, it's not like a common occurrence that somebody runs in that's so much more important than you that they skip the line. Computers, that would be very common, that we have an application that is more important. So that's why these guys are typically used in computers. Now, we do have different ways of implementing a priority queue. You can kind of think about this from, you could do this as just an array, right? You don't have to use a structure like this. You can just say, look, I'm going to have an array, and the guy who's at the front of the array, bucket 0 of the array, he's the most important. If somebody else comes in that's more important, I'm just going to shift everything down. I'm going to put him at the front. Otherwise, I'm going to place people as they come in where they belong in line, right? And kind of move things or make room for them, move them in, things like that. So we can implement this different ways, but we're going to be looking at this from the perspective of a binary heap using a binary search tree type thing as it's something that should look or feel something like a binary search tree to us. So common implementation of a heap is the binary heap. All right, so this guy takes the form of a binary tree, not necessarily a binary search tree. Binary tree, which says that a node has at most 2 children. All right, but because it's a heap, like we already mentioned, heaps have a generic property that effectively says we should be operating on full trees. As things get added to the heap, we are placing them at the next available location at the current level, at the current depth of that tree. And as soon as we run out of places, that's when we create a new row, if you want to think of it like that, a new depth in our tree. Okay. So in this particular case, if we were adding a new element to this tree, it would drop off the 3. And then the guy after that would be here. Guy after that would be here. Guy after that would be here. So on and so forth. All right. Presuming it's less than the 100. So things do need to go where they do belong. So that's where we have our heap operations here. All right, so we think to insert an element, and we are going to write a heap, but we'll start writing this after our break. So to insert, these are the steps for inserting into a heap. So we're going to add an element at the next location in the heap. Doesn't matter where it should belong. So here's this generic thing here. This is what our binary tree currently looks like. The very next dude that comes into this this priority queue, comes into this heap, he will initially be placed right here. That's the next open spot. All right. Then we're going to compare that added element with its parent. What is this? So some things that should start going through our mind here. What does this mean? Kind of like a doubly linked list, probably a doubly linked tree. We need to be able to talk to our parent, ask our parents some questions, right? We don't just have single directions going down the tree. Now we have the possibility of saying, hey, yo, Pops, tell me about your value because we might need to switch places. All right, that kind of stuff. So we initially place the guy here at this next open position, always going to go to the next open position. Then we compare the added element with its parent. If they're in the correct order, we're done. Life worked out. If they're not in the correct order, what do? We swap the element with its parent and return to the previous step. So if these guys are not in the correct order, let's see, do we have an example? Okay, so here's this. We are placing a all right, so if we're going to place a 15 into our heap based on this example, and we'll just finish this real quick. A 15 goes here. Then we say, oh, is a 15, is that less than 8? It's not. So we're going to do a swap. Then we say, is a 15 less than 11? It's not. So we're going to do a swap. So we follow this dude up the tree until he finally lands where he belongs, following that heap rule set. All right, that makes some sense? All right, so we'll review that when we come back from break. Remember, by midnight Wednesday, get the exam done. I'll have them graded by Monday when we come back from break, hopefully. Otherwise, I will see you next week sometime.